Hello, my name is Florian Achermann and I'm a PhD student at the Autonomous Systems Lab at ETH Zurich. Today I'm going to present you the paper MultiPoint Cross-spectral registration of thermal and optical aerial imagery. Detecting and mapping thermals remotely enables UAVs to plan their flight paths to maximize their range and/or flight time. We want to explore if thermals can be predicted using high-resolution multispectral maps. But creating such maps is currently limited by the poor performance of state-of-the-art multispectral keypoint detectors and descriptors. By proposing MultiPoint, we want to bridge that gap. To do so, we created a dataset of optical and thermal image pairs. We first collected the raw data using our UAV with downward-facing optical and thermal cameras, and then refined the alignment in a post-processing step. Then we used that dataset to train a neural network to detect and describe interest points consistently in both spectra. The data was collected in a region in Switzerland with a mix of farmed and lightly forested terrain. We conducted 10 flights at different times, ranging from early morning to mid-afternoon. Since the raw image pairs were not well aligned, we refined the alignment by maximizing the mutual information. However, this post-processing step did not always converge to good solutions, thus we filtered out the bad ones manually, resulting in a dataset of a bit over 13,000 image pairs. We split the dataset across flights into a training and test set. MultiPoint is a fully convolutional neural network consisting of an encoder and two specialized decoder heads, one for the interest point detection and one to generate the descriptors. This network structure was inspired by SuperPoint. It is trained using image pairs where the spectrum of each image is randomly sampled. This results MultiPoint observing multi-spectral as well as same spectrum pairs during training. Training MultiPoint this way yields higher performance compared to MultiPoint trained with only multispectral pairs. We also explored alternative network structure, such as this dual encoder structure, which had a specialized encoder for each spectrum. However, it compared similar to the single encoder network, and that is why we used a single general encoder for MultiPoint. MultiPoint requires keypoint labels for training. Those labels are generated using the concept of multispectral homographic adaptation. An unlabeled image pair is warped with a randomly sampled homography. Then for both images separately, a base detector, in our case SURF, is applied. To get the union of both keypoint sets, the heat maps are pixel-wise multiplied and then warped back into the original frame. This process is repeated with different randomly sampled homographies, and the resulting heat maps are aggregated. This leads to a keypoint superset consistent across spectra and viewpoints. We compare the performance of MultiPoint on the test set to our baseline methods. We observed that it outperforms all baseline methods significantly. While MultiPoint in general results in more correct matches, indicated in green, compared to SuperPoint and SIFT, there are still some cases, for example the bottom one, where all methods fail to produce good results. Finally, we applied MultiPoint to a raw image stream recorded by our UAV and generated same and multispectral matches. We used RANSAC to filter out bad matches. The results look promising, leading us to the next step where we want to utilize MultiPoint to generate consistent multispectral maps for thermal detection. The code to train, evaluate, and run MultiPoint, as well as the model and the dataset, are publicly available on GitHub.